Hey guys, welcome back. We're going to finish up this chapter with a game. So we're going to play Greedy Pig. Now in class, this is probably a little bit more fun to play this game in class when you're playing against other people, but I'm going to still try and show you the game, and I suppose you can play against me. We'll see how you do. And let's go ahead and get started. So it's a fun game and a good way to explain expected values. So we're going to roll a dice, and if we roll a 1 through 4 or a 6, then you get the number of points that we roll. But if we roll a 5, then you lose all of your points. So basically, I would have everyone stand up, and everyone will play the first round, I suppose. And we'll just do an example here. So we'll roll the dice, and we all have 3 points. Now, if you want to stay with 3 points because you don't want to risk it, if you feel like a 5's coming up, even though no one can feel it, right? Then you can sit down and play it very conservatively with only 3 points. Then at the end of 5 rounds, then we will add up all the points that you got for each round, and whoever has the most points at the end of the 5 rounds will be our winner, and we'll get some sort of prize. So right now we both, I suppose if we're playing against each other, we both have 3 points. I'm going to keep going. You can sit down with 3. Now if the next one is 5, and then I would be out, and then you would win. So you can do whatever you want. Just be honest. All right, so roll again, and it's a 5. So if you would have sat down on the last one with your 3 points, you'd be in the lead right now, and I have 0 points. So you also might have 0 points more likely, or if you sat down, then you'd have 3. Let's play another round. All right, so everyone's playing the first round. We got 4. I'm going to keep going. You can sit down with 4 if you want. We'll see what happens next. Okay, I'm going to keep going. I'm at 10. All right, I'm at 16. I'm going to stay with 16, but if you want to play risky, you can stop if you want, or keep going. So here's the next one. Oh man. Okay, so you're up to 22, or sorry, 22. So if you want to keep going, I'm just going to assume I'm going to keep going until we get to 5. How about that? So 22. So now you're at 26. I'm going to go again. 27, 28. If you want to keep playing, you can, or you can stop at 28. I mean, clearly you'd be winning if you kept going. Wow. Okay, so that's going to put us up to 34. And do you want to stop now? Okay, we'll keep going. Wow. Okay, so now we're at 40. 41. You want to stop now? All right, so the most you could have got was 41 out of that one. If you kept going and got 0, then I would be in the lead with 16 or 4 versus your 4, or wherever you stopped. We'll see. All right, so you see how the game is played. I guess we'll do a few more rounds, but this is all just time. So I'll let you skip to the end of the game if you don't want to. I'll put that in there. So, all right, so we're going to start. This will be our 3rd round. Okay, that didn't count because that wasn't a full round. All right, so we've all got 6 points. I'm going to keep going. If you want to sit down, you totally can. All right, 12, I'm going to keep going. Ah, man. Okay, so I totally have 16 points at this point because I lost the first one and I lost the 3rd round as well. So however many points, I have 16 so far. Let's play our next round. So that's 6. All right, I'm going to keep going. You can sit down if you want. Ah, man, I should have sat down. But hey, you never know, right? So I still only have 16 points. How many points do you have? That was, I believe, our 4th round. Let's do our last and final round. At this point, you know how many you have to beat. So you just have to make sure you have 16 points to beat me. Clearly, this game would be a little bit more interesting if you're playing against a whole class full of people. But, you know, COVID. All right, 3, I'm going to keep going. 5, I'm going to keep going. 7, hit me. All right, so 11. My strategy would probably be based on whoever had the most points at this point too. So 11, I'm going to keep going. Oh no. Okay, so I only ended up with 16 points. At that point, we'd be done. How many points did you have? Do you have more than 16? Then you beat me. Congratulations. This is a bit of a game of chance, but there is a strategy, and I may have already known the optimum strategy, and I was using the optimum strategy, and I still only got 16 points. Shame on me. Come back later and I'll teach you what the optimum strategy is. The game is called Greedy Pig. If you're really curious, you can look it up, or just wait. Actually, don't look it up because, well, it depends. If you're in class, then we're going to play this game probably more than once because it's a lot of fun. So don't look it up. Don't cheat. Don't do it. All right, anyway, fun game. We will talk more about it later, but think about it. So strategies. Can you time it? Should you sit down? When should you sit down? So is it possible to know when a 5 is coming? No, and because each time we roll a dice, it's independent. Even if it's based on a computer program like the one we were doing, that would be pseudo-random. So it's based on some random integers. It satisfies the test and the conditions for random. We know what can happen, but not what will happen. And in the long run, the empirical probability, we know that 1 out of 6 or 16.6 repeating percent of the time that we would get 5. So we can find the expected value. So that would be on average 1 out of every 6 rolls would be a 5. So should that mean that you should do the first 5 rolls and then stop after the 6th one because you know you'd be due for a 5? Well, that's not necessarily true. So how would we find that? How would we find out what our optimum strategy? Should you just play the room? Should you just play who you're going against? And so if everyone's still standing, you know that maybe you could stop if everyone's still standing, we could all lose the next round. So that would totally be fine, right? Because then you'd still be the same as everyone else. So would you play it really conservative? Would you only play 3 rounds every time and then stop after the 3rd dice roll? Or should you go further? I don't know. Think about your strategy and we'll play again. Develop a strategy. So after playing a few games, what do you think is the best strategy? Do you quit after some n number of rounds? Do you quit after you accumulated n points? Do you quit after n people or n% of people are still playing? So if half people sit down, that's when you decide to sit down as well. Or is rehab for quitters? Champions never quit unless it's capable. Then you quit that. So commercial. I don't know if you guys even remember that from last year. Or do you propose a different strategy? I don't know. Think about it. It's kind of fun. All right, 55A. So we're pretty much done with everything we need with continuous random variables and random variables in general. Just remember what we have with shifting, scaling, and then the last one, which is adding, using Pythagorean theorem of statistics to add random events together. So we're going to use those 3 concepts, shifting, scaling, and adding random events together with the Pythagorean theorem of statistics to do these next problems. So we're going to do 55 and 56. 55 is in the book, 56 is not, and then the back side you're going to try it on your own. So let's get started. A certain coffee shop, all the customers buy a cup of coffee, some also buy a donut. The shop owner believes that the number of cups that he sells each day is normally distributed with 320 cups and a standard deviation of 20. He also believes the number of donuts he sells each day is independent of the coffee sales and is normally distributed with a mean of 150 donuts and a standard deviation of 12. Alright, so it says that a coffee shop is open every day but Sunday. Assuming that day-to-day sales are independent, what's the probability he'll sell over 2,000 cups of coffee in a week? So what we have here is we have our daily amount that we're selling, and then we are doing that for 6 days because they're closed on Sunday. So the question is, are we scaling or are we adding independent events? So if we were scaling by 6, that would be, for instance, if we roll a dice, which would represent something for each day, are we taking whatever we get for the first day, like the Monday, and then multiplying it by 6, or are we rolling the dice 6 times and adding those together? So in this case, we're not just taking the coffee sales from Monday and then multiplying it by 6 to project what we would expect to have for the rest of the week. Instead, each one of those days, Monday, Tuesday, all the way through Saturday, would be independent events. So we're adding 6 independent events together. So in the dice example, the expected value for each one of those would be 3.5. So it would be 3.5 plus 3.5 plus 3.5 for each of the 6 days, so 6 times 3.5. And that's what we do for the expected value when we're adding random events. But whenever we have the variance between those, we're actually, instead of multiplying the standard deviation by 6, in this case, because we're doing the Pythagorean theorem of statistics, these are independent events, and so it's not going to quite be adding the variance, or multiplying the standard deviation by 6. Instead, we can look at it as either adding the variation together, so taking the variance, which would be 400, and then multiplying that by 6 and then taking the square root to get back to standard deviation, or you can think of it as a Pythagorean theorem where you're taking the standard deviation, squaring it, multiplying it by the number of days, and then taking the square root when we're done. All right, so let's get right into this one. So our mean is 320 per day, and if we have that for 6 days, what we do to find the center is do 320 multiplied by 6, and that's going to be centered at 1920. So we're expecting to sell on average for a week 1920 or 1,920 cups of coffee. The next question is, what would our standard deviation be? Well, for each coffee, each day is a standard deviation of 20. So there's 2 ways to do this. The first thing you could do is find the basically square it to find the variation. So for each day, the variation we would have is 400. And we can multiply the variation times 6, and then that's given us the total amount of variation we'd have in a 6-day work week. But then to go back to standard deviation, we would take the square root of that, which would give us this standard deviation of 48.99. Now the other way you could do it with like the Pythagorean theorem is basically we're doing 20 squared plus 20 squared again, plus 20 squared, etc. We're going to do this essentially 6 times. Now I'm just going to do it 3 times and then double it because I'm lazy. So that times 2. And then you notice it's the same thing we had before. Then we take the square root of it, which will give us back to standard deviation. And it's the same thing we had before. All right, so an even easier way to do it is that we can do basically 6 times in parentheses our standard deviation squared, and then whenever I'm done with this, I'm going to take the square root of it. Hey, doesn't that look nice? And then take the square root of it, which will give us, again, the exact same thing we had before. All right, so we have our standard deviation centered at 1920 with standard deviation of 48.99. So we can actually fill in the rest of this. We want to know the probability he sells over 2,000 cups, so we just need to go to the right side over here. So you can fill that, just add this number to it, and then add it again, and add it again. So it looks like what we're looking for is going to be a little bit less than 2 standard deviations above the mean, and we want to find the area under that curve. Well, to do that, we would use our normal CDF function. So that's in our distribution, so second variables. Distribution, the second one is normal CDF. Our lower bound for us is going to be 2,000. Our upper bound is going to be 9,999, which would be plenty of standard deviations out to get what we want. Centered at 1920 with a standard deviation, we said 47.99. I'm going to look at that again. 48.99. Okay, good thing I checked. 48.99. All right, then hit paste and good to go. So the probability of this event occurring would be 5.12%. Is that what I got here? Now, awesome, sweet. So whenever we're doing the AP test, we do want to, if we put anything in the calculator, we need to tell them what we put in. So the parameters that you saw that were put in the calculator right here, normal CDF, 2,999, 1920, then the standard deviation, that's what you need to show them. So again, that's our left bound. I guess I should have shown you that. So left bound was 2,000. We want to know anything above 2,000. All the way up to 9,999, centered at 1920 with standard deviation of 48.99. And that'll work. Next one, if he makes a profit of 50 cents on each cup of coffee and 40 cents on each donut, can he reasonably expect to have a day's profit over $300? Explain. All right, so what we're going to do is we're going to multiply each cup, because right now all the information we have is in units of cups. So the average is 320 cups with a standard deviation of 20 cups, and then the donuts are like units of donuts. So we want to convert that to the profit, which is the amount of money. So what we're doing is for every cup sold, it's going to be 50 cents. So we're basically multiplying this by 0.5, or a scale factor of 0.5. And if you remember, when we scale, everything's going to be shrunk. Just like scaling by a scale factor of 2, where basically the mean is going to be twice as big. Like taking a dice and multiplying it by 2 was 7, because it was 3.5 plus 3.5 or whatever, 3.5 times 2, which is 7. And then the standard deviation is going to be twice as wide, because the range is twice as wide and everything's going to be spread out by 2. So in this case, we're going to be scaling by 0.5, so it's going to be 1/2. So the average amount of profit he's going to get off the coffee is going to be $160. The average standard deviation is going to be half, which is going to be $10, right? 50 cents per cup, and the standard deviation now going to be 10. Now we have 2 things that we're selling, right? Not just the coffee, but the donuts. So we're going to have to add them together. But first, we're going to scale it. So the donut is going to be 0.4 times 15, which is going to be $60, and then 0.4 times 12 is going to give us $4.8. So the standard deviation for these two. Now, these are going to be the 2 independent events. Now that we've scaled them, the profit from the sales and the profit from the donuts are independent of each other. So to find the average, or sorry, not the average, to find the expected value, which is similar to the average, well, on average, what we would expect, right? We would add the means together. So on average, we'd expect to sell $220. So it's going to be centered at $220 with a standard deviation of what? Well, there's 2 random events going on here. So we use the Pythagorean theorem, or add the variations, in other words. So we're going to do 10 squared plus 4.8 squared, and then we're going to take the square root of that, and they're independent events, so we can do this, which is going to be 11.1. So a standard deviation of $11.1. So each day we're expecting $220 in profit with a standard deviation of $11.1. I hope he doesn't have any employees, because you can't pay your employees with that amount of profit. So I hope he's running this business by himself, and he doesn't have a family. But anyway, it's just an example. All right, so we scaled it by the profit. In this case, we want to know over $300. So, oh yeah, we need to go ahead and add the standard deviations to each one of those. Did I not do that part? Oh, there it is. So that's the standard deviation. Good to go. We're going all the way up to 300. Okay, 300, I believe, is more than 7 standard deviations above the mean. So that's not going to happen. If we put it in our calculator, we're going from 300 to 999, centered at 210 with a mean of that, and it's going to give us this value. Yours is going to say 2.87 times, or e to the negative 12th or something, which means that there's 12 or 11 zeros in front of it or something like that. So basically practically nothing. The probability of this occurring is not going to happen. So he's not going to have a daily profit over $300. What's the probability that on any given day he'll sell a donut to more than half of his coffee customers? All right, so this one's a little tricky. So the first thing we want to do is we want to multiply his coffee customers by half. And we want to see what's the probability that this is positive. So the difference between the number of donuts he sold minus half of the coffee sales. So if that's positive, that means he sold more donuts than he did half of the coffee sales. Hopefully that makes sense. So we're looking for the value of when this is greater than 0. All right, so in this case here, the half of the coffee, if we scale this by 1/2, we would have a mean of 160 and a standard deviation of half again, which would be 10, standard deviation of 10. So in this case here, what we're expecting, our difference between this donuts minus the coffee, would be negative 10. All right, we're expecting to sell 10 less donuts than half of the coffee sales. So in that case, so our center is at negative 10. Now the standard deviation, again, we had to scale this one. It's actually going to be half of that value. So the standard deviation for half of the sales would be 10. So we're going to do 10 squared plus 12 squared, and then when we're done, we're going to take the square root of that. So basically adding the variations together, then going back to standard deviation, which is 15.62. And so that's going to be our standard deviation. So we want to go, we want to know when donuts minus half the coffee sales is positive instead of this negative. So we got to go to the right. So we're going to fill in those values. That should be different. I think I did that wrong. All right, I fixed it. Okay, so we want to know when this value is positive, which means that this is going to be greater than, that's going to be 0. Okay, so we want to know the area under the curve going from 0 all the way to positive infinity, centered at negative 10 with a standard deviation of 15.62. So that's what we put in the calculator. So from 0 to positive infinity, we'll just do 999. That's plenty of standard deviations to encapsulate all of it. Centered at negative 10 with that as our standard deviation, which would give us a probability of 26.1% of the time. So 26.1% of the time we would expect to sell more donuts to a donut to more than half of the coffee customers. All right, 56A. So this one's not in the back of the book, but I'll do it with you. The Atlas Bodybuilding Company, ABC, sells starter sets of barbells that consist of 1 bar, 2 20-pound weights, and 4 5-pound weights. The bars weigh an average of 10 pounds with a standard deviation of a quarter pound. The weights average the specified amounts, that's nice, but the standard deviations are 0.2 for the 20-pounders and 0.1 for the 5-pounders. We can assume that the weights are normally distributed. So ABC ships these starter sets with customers in 2 boxes. The bar goes in box 1 and the 6 weights go in the other box. What's the probability that the total weight of the 6 boxes of the second box exceeds 60.5 pounds? Define your variables and clearly state the assumptions that you make. So on this one, I filled in this chart here. So the bar itself, there's only one of them, that's in the first box, weighs, on an average of 10 pounds with a standard deviation of a quarter pound. And then the weights, there are 4 5-pounds, which weigh 5 pounds on average with a standard deviation of 0.1. And 2 20-pound weights that weigh 20 pounds on average with a standard deviation of 0.2. All right, so we are looking at the second box, which is going to be 4 5-pounders and 2 20-pounders. So if we want to find the average, of course, in this case, so our average is going to be 5 times 4, or basically 5 plus 5 plus 5 plus 5, 4 times, which would be 20 pounds, plus another 20 and 20, which would put us at 60 pounds. So the average that we would expect the second box to be would be 60 pounds, so that's where it's centered at. Now the real question is, what's the standard deviation? So how far would that go out? Well, each one of these, each one of the weights is going to be an independent event, right? So you can't just take whatever assumption and multiply the standard deviation by 4. We're not scaling in this case. They're going to be independent events, so we have to use the Pythagorean theorem of statistics. So I'm going to do 4 times the standard deviation of 0.1, and then I'm going to square that. So this is basically going to be 4 times the variation for the 5 pound weights, okay? And then I'm going to add to that the 2 times the variation that we would have for the 20 pounders. And then, so basically you could do 0.1 squared plus 0.1 squared plus 0.1 squared 4 times, right? Plus 0.2 squared plus 0.2 squared 2 times, okay? So essentially that's what we're doing here. We're finding this is the sum of all the variation. And then we're done with that. We need to take the square root of it, which will take us right back to standard deviation units, which is 34.6. So yeah, all right, I did it right. Cool. So standard deviation 34.6. We want to know the probability that the second one weighs more than 60.5 pounds, so we're moving it to the right over here. So I add it, then I add it again and again. So 30.5 is going to be somewhere about right here. We want to find the area under the curve that is larger than that value. So we're doing the normal CDF, left bound 60.5, right bound 99, 999, or just 99 probably work just fine. Centered at 60 with standard deviation of 0.346. Let me show you how to put that in the calculator again real quick. So we're going to go, second variables of distribution, normal CDF, the second one. Our left bound is 60.5, right bound 999, is fine with me. Centered at 60 with a standard deviation of 0.346, and hit paste, and we get a probability of 7.4. So only 7.4% of the time we would expect to have the second box weigh more than 60.5 pounds. It costs ABC 40 cents per pound to ship the box containing the weights. Because it's an odd-shaped package, though, the first box containing the bar is 50 cents per pound plus a $6 surcharge. So the per pound is going to be basically scaling. So we're going to multiply the weights and the standard deviations by the scale of 0.4 and 0.5. But then we're also going to shift the weight for the first package that's being shipped by a $6 surcharge. Now that's not going to impact the standard deviation because all of that's shifted just to the right by adding $6 at the very end. So we'll do that part at the end. So the first thing I want to do is actually scale. So the bar was 50 cents per pound. So the weight would be on average $5, right? So 50 cents times 10 would be $5. A standard deviation of a quarter of a half, half of a quarter, whatever, is going to be $0.125. And then the weights themselves were 40 cents, so we're going to scale that. So 0.4 times 5 is going to be $2, and 4 cents would be our standard deviation. And then 20 pounds times 0.4 is going to put that at $8, and then this would be 8 cents. All right, so next thing I want to do is I want to find the expected average cost. So for the bar, that's going to be $5, and then plus 6 more would be $11. And then $8 more, which would be 19, and then 16 more dollars, which would put us at 35, because there were 2 of those and 4 of those, right? So on average, we're expecting it to cost $35. Then the standard deviation, that's where we're definitely going to need the calculator for that part. So for the standard deviation here, we have, these are all independent events. There are 7 things altogether that we are shipping, so we're going to have all of that here. We're going to do the Pythagorean theorem with 7 different things, but I'm going to try to combine it as best I can. So we have 0.125 squared, plus there are 4 of those, so 4 times 0.04 squared, okay, close the parentheses, plus 2 of them, so 2 times, in parentheses, 0.08 squared, and then close parentheses. All right, so that's going to be the total variation. We have the variation for the first item, which is a bar, the 4 5-pounders, plus the variation that we have for the 2 20-pounders. So that's the total amount of variation. When we're done, we want to take the square root of it to go back to standard deviation units. So that would be 18.67 or 0.66. I think if we didn't round. Oh, we did round. It just rounded down. Okay, cool. So that's our center with standard deviation here. From there, we can find the probabilities, but they didn't ask for it on this one because it's enough work as is. Last one we're going to do, number C, or part C, number C. You can tell it's late. I need to go to bed. All right, suppose a customer puts a 20-pound weight at one end of the bar and 4 5-pound weights at the other end. So although they would expect the two ends to weigh the same amount, they might differ slightly. What's the probability that the difference is more than a quarter pound? So on this one, of course, the expected value, so 4 times 5 is going to be the same thing as a 20 pounds. So we would expect a difference of 0 pounds. So we're going to center our model at 0. What we're going to do is we're going to take the difference between the two. So the 20-pound minus 4 5-pounders. So even though we're subtracting the difference here, the variations are still going to add together, but our expected values are going to be subtracted. So the expected value of the 20 was averaging 20, and then 4 of the 5s would put it at 20. So the difference between the two, of course, is going to be 0. But the variation is going to be added together even though we were subtracting. So I'm going to take the variation of the 4. It's basically the same thing I had here, right? No, except there's only one of those. But I'm so lazy, I'm going to do it anyway. Yeah, all right, so we have one 20-pounder. No, that's cost. And I can't do that. Sorry. Delete. Okay, so I tried being lazy. But we have 4 5-pounders. So 4 times the 0.1 squared for the variation for each one of those. And then we're going to add the variation that we have from the 0.2 squared. Okay, and then take the square root of all that. Okay, cool. So 28.28, so 28.3 if we want to round. So that's our standard deviation. We want to add that and subtract it from both sides because we're interested in both sides. And then, so on the diagram, we want to go from negative quarter pound difference all the way to a positive quarter pound difference, which would be about right there. So we want to go from negative infinity all the way up to a difference of negative quarter pound, and then we want to go to a difference of a positive from positive infinity to that. So the probability that it's more than a quarter pound off is going to go on both sides. So we actually can't put 2 tails into the calculator like that. So instead I'm just going to calculate one of the tails and then multiply it by 2 because it is symmetrical, so that'll work out just fine. So in our calculator, we're going to do second distributions, the second option. I'm going to go from negative infinity, so negative 999, all the way up to a negative quarter pound. So again, make sure you're using a negative symbol. Centered at 0 with standard deviation we said of 0.28 something. Let me check that real quick. 0.283. All right, so 0.283. All right, so the probability of that occurring is going to be 18.85. So that's what we put in the calculator, 18.85. Now remember, I have to multiply this by 2 because there's 2 tails, and that'll give me a total of 37.7%. All right, so you can take that value, multiply by 2. There you go. So 0.377. All right, I think we're done. Yeah, totally done. All right, so let me know if you have any questions. Try the back side on your own. So on the back side, isn't this fun? All right, so try the backside on your own. It's not in the book, so you really got to make sure you know how to do it. So try not to leave it blank. If you get stuck, let me know, and I'll see you guys later.